we've seen now that if beta is the angle is measured counterclockwise from the downward vertical direction to the r vector being from the axis of rotation to the point where the small mass m is attached to the wheel, that the equation that we see here applies to that motion. Okay, the beta double prime means the second derivative of this angle beta with respect to time. The k is your k vector, and you have this restoring torque. The solution to this equation, this analogous to the solution of mx double prime equals negative kx, is this. Okay? And it looks exactly like the solution we get for simple harmonic motion in on a spring or whatever. The amplitude is going to be an angular amplitude, and omega is going to come out of this equation rather than this equation. In this equation, remember, omega was the square root of k over m. In this equation, it's going to be the square root of this mess over moment of inertia. And we also have the k vector to indicate the direction of the torque and of the angular motion and so forth. Okay, here's our omega. I don't think I wrote the square root when I did this in class, kind of make note of that. And we get angular simple harmonic motion with angular frequency omega. Frequency then omega over 2 pi, omega being the number of radians per second, frequency being the number of complete revolutions per second. Got to divide the number of radians by the angle of a revolution to get the frequency. Okay. The angular amplitude is going to be what? Well, for this motion, in the case where the wheel is initially stationary, if x naught is the x-coordinate of the point P, then the angle here is what? It's going to be the arc sine of this divided by the radius, which is the radius of the circle, by the hypotenuse, which is the radius of the circle. So it should be very clear from this picture that if this is the extreme position, which it will be if the mass is placed here and then the thing starts rotating, this is going to be the inverse sine of x naught over r. Okay, that's going to be your amplitude. It's going to be your maximum angular displacement, your maximum value of beta. So that your beta of t will be that amplitude, inverse sine of x naught over r, times the cosine of omega t, plus some phase angle, depending on when you start your clock. Then we get our omega of t and alpha of t functions, our angular velocity and angular acceleration functions. Now I'm using capital omega here because I've got a small omega here that's what we're using for our angular frequency on our reference circle, which has nothing to do with this circle. So we need to use a different symbol, so I use capital omega instead of the lowercase omega that we usually use for angular velocity. In any case, this is a derivative of this, and this is a derivative of this. So we have our position, angular velocity, angular position, angular velocity, angular acceleration functions. Now a question, okay, now that we have this, now that we've been through all of this, we know everything we need to know about how the wheel rotates. Now if we have some initial conditions and so forth, we work those in, but we have these equations, and the only variables in this situation for the whole given disk and everything are the phase angle phi, which depends on where the wheel is when you start your time, and your x naught, which also depends on where the wheel is when you start your time. Actually, your x-naught doesn't depend on where the wheel is when you start your time. It's going to be your maximum displacement in the x direction from the equilibrium position. Okay. Well, you're asked to find the kinetic energy. Okay. What's the kinetic energy? Well, as soon as you hear kinetic energy, you probably think 1/2 mv squared. I hope you do. Unless you happen to know that, okay, in angular terms, it's going to be 1/2 I omega squared. That would be a reasonable thing to hope for. Okay, because this is what we're going to have to use to get the kinetic energy as a function of time, and that's requested. Well, that's very easy. And ask people to write that out. I assume people did that correctly, except here we're using capital omega for the angular velocity, and that is the omega that we use when calculating kinetic energy, so I better say big omega squared. In that case, it'd be 1/2 I times the square of this mass. And remember now, I is part of little omega, right? This little omega here. So that when you square this big omega, you're going to have a squared little omega, which means you're going to end up with the square of this expression, which is going to put an I in the denominator. And there's an I here that's going to divide this I, and the I's are going to kind of disappear here from the kinetic energy. And then it'll be in terms of mass little m and yeah, that shouldn't happen. Okay, well, it can, yeah. Because of the units of these quantities. No, it shouldn't. Well, you work it out. Write the thing out and see if it does what I just said it does, because if it does, there's a problem here. And then think through the problem. We'll deal with it later. The total energy is the kinetic energy at the time when the sine of omega t plus phi is plus or minus 1. It's the biggest the sine can get. The squared sine is going to appear up here and so forth. So if you write the expression out, you can get the total energy just by replacing your sine of omega t plus phi with either a plus or minus 1. You're going to have a squared sine, and even if you use a -1, it's going to come out positive. Now, you're also asked then to verify that that's equal to the gravitational potential energy at this point relative to this point. So how would you calculate the gravitational energy here relative to this point? Well, you can take the definition of gravitational potential energy as equal and opposite to the work done by the gravitational force. Okay, the work done by the gravitational force is going to be, well, if you go from here to here, it's going to be this vector, okay, projected onto your weight vector, displacement vector here, project onto your weight vector, etc. That projection is going to just be this vector, so if you just multiply this distance here by the mg, you're going to get potential energy change, okay? And use that to get your gravitational potential energy and see if that isn't equal to this. And that will come out in units of mg times distance, okay? Force times distance, work, energy. So when I said there's a problem up here, there isn't, because it comes out in units of mg, which is force, times r, which is distance, which is energy. Okay, so this is an important picture. Make sure you understand this. Okay, and yeah, just to get your work done by gravity, you've got your mg vector. You've got your delta S vector, if you project your delta S vector onto your mg vector, here's the projection. So to get the work done by the mg force through the displacement delta S, you multiply the mg force times this displacement. They're in opposite directions, so you're going to get a negative. And that's the same as multiplying the weight by this displacement here. Think about that. Get used to that picture, get used to that idea. It's very helpful in analyzing a complex situation.